What is work done? Which one is correct? Is it half force times distance or force times distance? Here we will see how work done is really done. We'll start by the first part, half force times distance. A much more common type of work that is encountered in structural engineering is work done through the deformation of structural parts. If a load is gradually applied to a bar in tension, then the displacement of the right side of the bar increases gradually in proportion to increasing applied force. Here we see that the area, the shaded part of the area, is the force times the displacement, half. Now, if the material is elastic, then the displacement is linearly related to the force. We apply Hooke's law, K times delta. When P is applied into the structure, the force, and K is actual stiffness, and D is a deformation of the bar, the work done in displacing the right end of the bar is equal to the area under the force versus displacement. We've seen the internal work done. We now see the external work done. Notice that this is similar to the general work equation, but it is divided by 2 because the area under the plot is a triangle instead of a rectangle. This new equation for work is applicable when the displacement is linearly proportional to the added force, P. That is when the force is directly causing a deformation. The work caused by the external force, P delta over 2, is called the external work. In any closed system, energy can never be created or destroyed. We just have to recall conservation of energy from physics. Since work is a type of energy, any external work energy that is applied must go somewhere in a structure system that is deformed slowly. The external work energy is typically converted to strain energy in the structural members. This strain energy can also be called internal work. The total strain energy in a simple bar that is deformed axially by a force that gradually increases from 0 up to a maximum force P, as we can see from the drawing, is equal to P delta over 2, of course, where delta is the actual deformation of the bar. What if we now add another force to the bar, a new force Q, while keeping the original force P constant? We just have to see a force does not have to be directly the cause of displacement or deformation in order to do work. As we can see, the P is doing work. A force on a structure can do work, even if it's just along for the ride. In this figure, first, a force P is gradually added to the bar. The external work done by this force up to a deformation of delta. Here we see that this deformation here, this part here, the work done is P delta over 2, where delta is a deformation of just because of the load P. This is a lighter shaded part of the area. It's the same as the work done previously that we saw. Now, the external work done by the additional of the force Q, which gradually increased from 0 up to maximum value, is similar to the original work that was done by force P when it was applied. So these two they have similarity, of course. This work done is delta Q times delta, of course half of it. The original force P continues to do work as bar is deformed, even though the force P has not changed, and even though it is not causing the change in the deformation, the amount of work done by P is, in this situation, as Q is gradually applied, is not the same as it would have been if it was P that causes the new deformation. Since the force P is constant the entire time that force Q is applied to the bar, the additional external work caused by the force P is equal to P times delta Q. So that deformation caused by Q times the original load P is the work done by it, or the force P. This is a dark shaded area of the triangle area. Notice that the type of work where the force doesn't cause the deformation, there is no more factor half in the work equations. Since the area is rectangular instead of triangular, this distinction will be important in development of the principle of virtual work. I mean, we have to add the triangular part into here, and then we cause a linear form of deformation. The virtual work method is a method calculating deflection. It can be used to find the deflection of truss, beams, or frames. In fact, any mechanism and the deformation of linear axial element is equal to where we see PL over EA, where L is the length of the bar, E is the Young modulus of the bar material, and A is the cross-sectional area of the bar. If there is only one bar in the system that we've seen earlier, then the total internal work or strain energy in the system is equal to this part here. Well, we see, let's show you here. Yeah. Now we equate the external work done with the strain energy inside the bar. Since the energy must be conserved in the system, all the work that is applied to form these equations from outside must be balanced by the work done on the inside of the strain energy. All the external work must equal to the internal work. This is true as long as all the energy in the system is in the form of work and strain energy. It will not apply if some of the energy is kinetic energy or structure is moving dynamically at some non-zero velocity, or if some of the energy is dissipated as heat. So for the system, the external work is equal to the internal work, which is equal to the strain energy in the bar. From there, we find the deflections of the bar. So this is what we use mostly to do our virtual work method, to work out the deflections of especially we used it in my earlier portal frame videos. You see how rotationals and then displacements are used to work out the strain inside the strain energy, and then to be able to work out even MPs. In this case, we can work out the deflections of the structure. Here we come to the second part of the work done, which is force times distance. Of course, the work in virtual work clearly implies energy, since work is one form of energy. Work is energy that is required to move mass around in space. The expression we use for work is like work force times distance, where P is a force on a body or structure, or delta is a displacement of that body or structure. The result in unit is like kilonewton meters here, what we saw. So if we just see this, how the structure is moving in a distance d. This is a normal work done that we are actually using. We can now conclude that with both equations, one is for structurals, the other is a normal work done. A virtual work method is a method for calculating deflection. It can be used to find the deflections of truss, beams, or frames, or in fact any mechanical system. Work can be expressed in terms of energy. The unit is like kilonewton meter, or 1000 joules is 1 kilonewton meter. In a rotational, work can also be defined as a moment multiplied by rotation, m theta, as we saw on my previous portal frame analysis, where m is a moment acting on structure and theta is a radian. It's a rotation. It has no unit. It's not degree or whatever. So we still get a kilonewton meter. So since rotation is effectively unitless, I mean, we get a moment theta rotations as a work done. A much more common type of work that is encountered in structural engineering is work done through the deformation of structural parts. This is part A of the calculations. If a load is gradually applied to the bar in tension, then the displacement of the right side of the bar also increases gradually, as we saw in the beginning of this video, in proportion to the increasing applied force. Of course, we can apply a load in a column type of structure as a tip. If deflects a levy, and that deflection times the external applied force is dissipated through the column into the joint, to the base joint, and cause a rotation. So that rotation radian times the moment is a deflection, is the internal force is equal to the deflections times the moment at top. So that's what will look like. Thank you. If you like this video and you want more of this, please don't forget to like, share, and subscribe. And